Hi there, we are Project Prometheus of UCLA Rocket Project, and we are competing in the 2021 IREC SRAD hybrid competition using our SRAD hybrid rocket system named Athena. I'm Ivan, one of the project co-leads.
And I'm Suman, the other project co-lead. Our team is broken up into the three major subsystems: propulsion, vehicle engineering, and electronics, with 2 people leading each subsystem. From there, each subteam is further separated into individual components with their own respective leads and members. Our team has worked incredibly hard this past year in spite of the pandemic to present Athena. The system is designed to reach an apogee of over 8,000 feet using our SRAD hybrid engine housed inside of our carbon fiber monocoque vehicle structure. We will be delving deeper into the subsystem, starting with propulsion.
Hi, I'm Jackie.
And I'm Connor.
And we're the propulsion subteam leads. And we're going to get into talking about the propulsion system. So to start, here's a quick overview of our SRAD motor. Here you can see we have the aux tank, then we have our plumbing bay, and then our combustion chamber. And then here in our combustion chamber, we have our fuel grain, which is an HTPB mixture. And our motor is expected to have around like 950 pounds of thrust. Okay, onto our pressure vessel. Here you can see we have a vent hole at the top end cap. We have our tank. Then we have our bottom end cap with a nitrous port and some longeron fasteners. Then onto the end caps, we have 2 sets of redundant O-ring grooves on each end cap. We also have some retention bolt holes, which help with motor retention. And then our vent hole on the top end cap. And also these O-ring grooves help with just overall sealing for the tank. Then for our internal plumbing, here you can see this is the bottom end cap, our internal plumbing bay, and then our injector plate. And so here the nitrous flows through the bottom end cap, through our main propellant line into the combustion chamber. And then you can also see our fill line quick disconnect system attached here. So then a little bit more on the fill line quick disconnect and injector valve. Once again, you see the Bimba QD system, which is connected to our main propellant line. And we have our pneumatically actuated ball valve. Then last, for the internal plumbing, we have our vent line, which is attached to the top of our aux tank. And we have a line that runs down to our internal plumbing bay. And this ball valve is controlled by our pneumatic system.
All right, so next up is sort of an overview of our combustion chamber. So you can see on the far left here, we have our injector. Then we have a pre-combustion chamber that's lined with ablative. Then we have our fuel grain. Then we have another post-combustion mixing chamber. And then we have our nozzle. Here you can see our ignition setup. We have Pyrodex pellets that we're going to be using as our igniters. Those are connected to E-matches that are connected to electronics wires that will flow out through the nozzle, and we'll use those during ignition. Next up here is sort of a view of our injector. You can see that we have a large flange up here to connect to the rest of our internal plumbing system. You can see that we have bolt holes here to connect up to our combustion chamber. And then at the bottom here, you can see arrows representing our impinging injector. Here are some images of our water flows that we did with different injector designs. This is a shower head baseline design that we did during our design process. Then you can see these 2 impinging injector designs that help us sort of come to our final design and orifice count with the data that we collected from these tests. The nozzle that we're going to be using is from the M1575 commercial contrail motor. It includes a graphite insert that connects into a aluminum nozzle. Here is an overview of our plumbing system, P&ID. You can see that we use 3 bottles during our fire process. We have a nitrous bottle for our oxidizer. We have a nitrogen bottle for our leak checks that we do pre-fill. And then you can see we have a nitrogen bottle that we use for our pneumatics to control our vent and also our main propellant valve and our quick disconnect. Here is a CAD image of our plumbing box. You can see here that we have our nitrous line here. We have our leak check nitrogen line here. And then we have our pneumatics line here. And all of these lines are controlled by solenoid valves. And a very cool fact about this system is that this box here is all fully assembled currently. Thank you all so much. That has been the overview of the propulsion system.
And now on to vehicle engineering. My name is Logan Cheney, and I'm one of the vehicle engineering leads.
And I'm Ken Hollingsworth, and I'm the other vehicle engineering lead.
Once again, here is a photo of our CAD assembly and our open rocket, as well as a section view showing the layout of all the internals of the rocket. It's constructed out of carbon fiber, fiberglass, plywood, and metal, as well as 3D printed materials, including PETG.
The design of our airframe relies on 4 carbon fiber body tubes of varying length joined by couplers and plywood bulkheads supporting all internal features. One of the highlights of our aeroshell is the plumbing door, which is used to run lines of the quick disconnect lines to the motor's internal plumbing. This door is cut out of the carbon fiber airframe and is designed to close automatically using magnets.
And here's our nose cone, and it is constructed using an LD hack, also known as Von Karman geometry, to minimize drag. And you'll also notice that it's made out of fiberglass, PETG, which is 3D printed, and metal, aluminum specifically. And the fiberglass and PETG are RF transparent, which allows the rocket's GPS and telemetry to then communicate with our ground systems. And we also decided to manufacture the metal tip to be sharper, tougher, and create a more uniform shape at the top of the rocket. This is manufactured out of aluminum and provides superior material properties as well as aerodynamic benefits.
Going into the deployment of our recovery, it'll be using single bay dual deployment. How it'll work is the drogue chute will launch at around apogee around 8,000 feet, and the main chute will deploy around 1,500 feet. We'll also be using a 3 12-gram CO2 canister peregrine system, and also using the altimeter and redundant electronics. And going into the avionics aspect of it, the parallel circuit consisting of 2 altimeters and 2 batteries, which creates redundancy to ensure fail-safe in case either fail. And there will be a screw switch, which is simple, cost-effective, and which is more resistant to being accidentally turned on or off.
And here are recovery and thrust bulkheads. So the recovery bulkhead is on the left, and you can see that it has cutouts for the ejection system for recovery. And it is designed to bear the full load of parachute deployment, which is about 4,000 pounds. And in order to create bulkheads capable of withstanding such a load, we used multiple sheets of plywood to stack them all together to support that. And as well, you'll notice that on the right, the thrust bulkhead using a similar design, which is then responsible for varying the load of motor retention during launch, using those 4 bolts to fasten it into the top of the aux tank to support it. And as well, within each one of them, you can see a pin housing box, which is constructed out of metal, and that connects to the shock cords so that during recovery, we have it connected to the parachutes. And notice also in our report, we talked about other designs that we considered, including I-bolts and U-bolts, and we found that the pin housing was by far the best at withstanding these loads. And here are the longerons connecting the aux tank to the combustion chamber. They support and transfer the forces between the aux tank and the combustion chamber during launch, and are very crucial for supporting the engine. And they're the primary load-bearing structure designed with the assumption that the maximum load due to drogue deployment is perpendicular to the rocket, and we calculated that to be about 10,800 pounds force.
And going into the fins and boat tail, for our fins, we designed them with a curved airfoil profile on the leading edge and hexagonal airfoil on the trailing edge. We have 4 fins that are radially symmetric around the boat tail, and for the boat tail itself, it will be 3D printed and the fiberglass layup around the side.
Hi, I'm Alex McDermott.
And I'm Tracy Vu. We're the electronic leads that will be walking you through this next section.
The payload for this rocket is the cosmic ray detector inspired by MIT's Cosmic Ray Detector project. It detects cosmic radiation created by muons, which are subatomic particles created from supernovas in Earth's atmosphere. We are able to detect these muons through a plastic scintillator that turns the muons to photons. The silicon photomultiplier helps observe the photons and creates an electric current, which the main PCB amplifies for the Arduino to process and store in the SD card. Our main theory behind this payload is that as the rocket reaches higher altitudes, we should be able to detect more muons using the cosmic ray detector. We structured our payload to meet the competition's 3U CubeSat sizing, as well as the weight requirement of a minimum of 4 kilograms. The stack design allows for easy assembly as well as adaptability for future payloads. The payload has 2 aluminum plates capping the structure on each end for extra security. In between are 2 modules, with one holding the cosmic ray detector and the other containing the power bank. The payload is secured with threaded rods and lock nuts to hold everything in place. Our ground support electronics can be split into 2 subsystems, which are controls and data acquisition. Our control system can manage all of the solenoid valves in the ground plumbing system as well as ignition. We've also included multiple safety features into our system. An emergency shutoff switch, which cuts power to our system and turns the valves to their unenergized state, is located in the switch box. We've also included an arm switch located in the pad controls box to give pad personnel independent control of their safety. An LED light is also incorporated with the arm switch to inform us of powered lines. In addition to this, we also interlocked our final ignition switches. This ensures that one-time actions like flipping the fill line disconnect switch, arming ignition, and flipping the ignition and aux flow switches are always performed in the correct order.
With our data acquisition or DAC system, we have the ability to take pressure, thrust, and temperature data from multiple locations during a static fire or launch. All communication for both controls and data acquisition is protected by checksums and makes use of serial communication over Ethernet cable with the RS-485 and Modbus protocols to account for the distance of transmission. We've developed a program in MATLAB to store and graph all sensor data live, so operators always know the state of the rocket. For onboard data collection, we'll process data from sensors with a Feather microcontroller, then transmit over 433 megahertz radio and store on a micro SD card in case of transmission issues. On the ground, we'll receive data from the rocket through a Yagi directional antenna, giving us extended range. Data is then read into a microcontroller as a serial stream and then sent to a computer for live visualization and storage. Looking at the onboard data path diagram, you'll notice that our GPS is integrated with a 3G cellular module. This is a new technology for Project Prometheus. Text your rocket, the future is here. GPS data is sent both over radio and through SMS texts. If one fails, we'll still receive coordinate data through the other, increasing the likelihood of rocket recovery. Our other sensors, including an altimeter and inertial measurement unit, or IMU, measure altitude, pressure, rocket orientation, and acceleration. This suite of data allows us to verify the rocket's apogee, thrust, recovery forces, airspeed, and time of mission events. We can also track the rocket's angle of attack throughout flight. Already, we're happy to report successful line of sight transmission for up to 1.7 miles and have additional testing planned with less geographic constraints. The electronics housing fits in the nose cone of the rocket and is designed to house every electronic component in a safe, accessible manner while minimizing unoccupied space. The use of 3D printed modular pieces allows extra versatility and rapid replacement of individual levels in the event that components need to be swapped or repositioned. Additionally, an aluminum encased and foam-filled black box mounted to the bulkhead protects the SD card in the event of recovery failure.
Thank you so much for reviewing the hard work that our team has put into the Athena rocket system. We had so much fun putting this together for the competition, and we hope you enjoyed it.